So I want to end today by talking about a really neat philosophy. About prime numbers, which is that primes are, of course, completely deterministic. Right? I mean, there's some concrete list of primes, and we've discussed a couple ways that you could start writing it down if you wanted to. But in many ways, primes behave as if they were random. And this is actually a philosophy that goes quite deep in a lot of the results about prime numbers. There are a lot of results about primes that you can conjecture just from this philosophy, that primes behave as if they were random. And you can actually predict. And sometimes I think it gets involved in the proof methods as well, that you can treat primes as behaving randomly. So let's see a nice little example of this. How do primes behave mod m? So what I mean is, if you look at the set of primes, and you look at what they are congruent to, mod m, so which numbers 0 through m minus 1 they reduce to, what do you expect that distribution to be like? So from this philosophy, we expect an even distribution. In fact, this is totally true. So let me write this down in an informal way, but apart from obvious exceptions, primes are distributed evenly mod m for all m. So let me say what I mean by this using an example. So for example, let's look at mod 10. So what does z mod 10 look like? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the elements of z mod 10. And so first of all, what do we mean by apart from the obvious exceptions? So what I mean is that if you are 0 mod 10, then you are divisible by 10, and you are not prime. Because you're, so divisible by 10. If you are congruent to 2 mod 10, not prime, divisible by 2. And same with 4, same with 5. So 4, you're even. If 5, you're divisible by 5. 6, you're even. And 8, you're even. So primes can be none of those things, except for 2 and 5, which are the only ones that fall into those two slots. Apart from 2 and 5, there are none. Okay, but this leaves us with 4 possible things that a prime can reduce to. And the theorem is telling us that for these ones, we get an even distribution. So a quarter of primes are congruent to 1 mod 10. And then another quarter are congruent to 3 mod 10. and then another quarter are 7, and another quarter are 9. So what do I mean by 1/4 of primes? I mean this in a similar sense that we were talking about earlier with the prime number theorem. So if you look at the proportion of primes up to some fixed number and look at how many are 1 mod 10, it will be about 1/4. And this is also what I was referring to when I mentioned at the beginning of the lecture, are numbers ending in 7 more likely to be prime? This is telling us that, okay, well, first of all, every prime ends in 1, 3, 7, or 9, except for the 2 exceptions, 2 and 5. But among these last 4 digits, all of them occur about equally often. So this is a very nice example of why I think, primes, the theory of, working with prime numbers is very beautiful and very interesting, because there is this wonderful interplay between primes having lots of structure on the one hand and primes acting very randomly on the other hand. And this makes the theory sort of very rich and interesting.